Alright, so let's talk about the design of the truss house system that we've shown here. We're going to walk through the CAD, we're going to walk through the introduction documents, and then the part tree. So this is what we're going to be designing. It is a building slash house, however you want to call it. It's got two sides of its roof there, one of which has some sunroofs cut into it. It has a set of 5 trusses, each supported by 2 risers held in 2 concrete blocks. On each side there are 3 braces that run the length of the building and transfer the weight of the roof down to the truss, which is then held up by the risers. So what we're going to do is show how this is designed in CAD and how those designs are sent to Onshape, which is what you're looking at here. This is the Onshape CAD model. So let's just cover some quick terminology in Onshape. This is an assembly, as denoted by the icon there. The entire file, or URL, is called a document in Onshape. Each part or assembly is called an element. So you have a document that contains a bunch of elements, and within each element you can have multiple parts. We don't recommend this for working with CAD because it's just easier to keep track of the variables you're sending to specific parts when you have only one part. That also is much better design intent, and design intent is a CAD term that basically means that the model is driven by the parameters you want it to be driven by, and that's going to be very important for our purposes in this design. So here's the finished product. So the way that we did this in CAD was that we created each of our little parts. We created what I call the truss system, which is just the concrete blocks, the riser, and the truss, and then created another assembly that has 5 of those truss systems, the braces, and the roof. I'm going to cover how each of these is attached, but it's those attachments in the setup that's driven from Onshape. So driven by CAD. So let's go over to CAD. We are in the projects workspace in the structural systems folder, and this is our HouseTruss roof design. So in this workspace we have the introduction document. A document holds measurements and inputs, a workflow, and then the part tree itself. So it's often handy to write an introduction document. This is where this video will be, obviously. We just talk about what it is you're going to be designing, what the components are, and the general process for designing it. You're also, a sort of best practice is to have this separate measurements and inputs document. So this is what I would call a controlling document. This is where you set parameters like material properties, anything that's specifically related to the overall design. So as you can see here, the length of the house, the width of the house, the angle of the roof thickness, some properties that are fed into size the windows, the material density and material strength. So our trusses hold up the weight of the roof itself, but in real situations it's going to have to hold a dead load like snow, a wind load, a number of other things. So we have that factor here. And then there's always a factor of safety when you're designing something like this, which is just a multiple factor, so you can ensure that what your design is going to be able to actually do what you want it to do. So once you've established these properties, there's a link to CAD here. Open this dialog, and as you can see, this is the document that these are going to. It's all that same HouseTruss. This is the element, and then these are the equations that we're sending to it. We're sending the length of the house to some. So like from this document to the 2 sides of the roof, we send the length of the house and the roof thickness. To the one that's got the windows, we send the window properties. There are obviously properties sent to these items from the design documents, but since this is the major controlling document, the main parameters are sent from this document. So obviously the truss is the main thing that we're designing here. We send the width of the house and the angle of the roof from this document. Now those parameters are pulled into the design document for the truss as well, but they're sent from this document. Okay, so this is what controls everything. So let's open up the part tree. So we've linked all of these items up to our Onshape model. If you are logged into Onshape, you will see these icons. If not, you won't have permissions to see them, so they won't show up. It's still linked. So what this allows us to do is a number of things you're going to see here in a second. So let's start by opening up one of the simpler designs. Let's say the roof half here. So what we've done is we've pulled in the house width and the roof angle. We calculate the width of the roof. And then we have a variable called mass, which just holds the mass. We pulled in the density from that design document, and then the weight. We have a second one, which is the same number, which we call roof half weight, because we're pulling this weight parameter into other documents. And we want to be able to know, we want to be able to have a unique name in those documents. Now, notice again, we have this generic weight variable in every document. You're going to see why here in just a second. So by calculating variables named weight and mass in our documents like that, this lets us go into this column and pull out those equations. So what this does is it goes into each of those documents, pulls out that variable for parts which have their own documents, and for systems which don't have documents, it's the sum of all of these items. So this is the weight of each part summed up here. And so for the entire system here, there's say 10 of these concrete blocks, one at the bottom of each riser. So we've set that parameter there, and that's a multiple factor that's used in the calculation of the weight. We can also pull the weight directly from the CAD file. There's obviously going to be some deviation in the numbers here, but it should be pretty close. You shouldn't have more than a few percentage deviation. So let's look at one of the more complicated ones, the actual truss design. So we calculated to the weight of the roof itself in its design document by just multiplying the length, width, and depth times the density times gravity to get the weight. We pull in a number of parameters into this document. So here's all of our parameters that we're pulling in. You see the dead load from the design document, the safety factor, everything we're going to need. The process, which I won't go through each step of it, was you have the general layout of the truss. This is where the braces actually meet the truss. The roof is above the braces, and so that's where our load is applied. We calculated the spacing of each of these connection points, and then we calculated the load for each point. And what you figure out is that the same weight is applied at each point here. There's a brace for each side of the roof here, so it's the full weight is applied overall at the same point there. So each of these point loads is the same, and it comes out to this value for the current roof and dead load. So then what we do is we take a look at each part, and the parts in blue here are actually holding no load. Then we model it as a pin on one side and a roll on the other side, and this is one of our free body diagrams. So what we've done here is pulled in a line for each one of the lines you see here. Each one of these little blocks is text, and there's an image that we pull from our stock images folder to represent the pin and the roller there. So you can change these properties, you can change what it is you're looking at, and all that's covered in the free body diagram tutorial. Then we solve for the reactions at each side. Then we do the method of joints analysis for each joint, going from left to right. So we go A, H, B, J, C, L there. The one thing you have to really remember when doing this, obviously, is to keep your directions uniform so that when the values come out positive or negative, it's consistent across all joints. And so what you can see here is we've used symbolic equations to derive the formula and then solve the formula mathematically. So then we then take the load in each member that we've calculated and pull out the maximum one and use that to, along with the yield stress of aluminum and our safety factor, to calculate the minimum thickness. This is a square cross-section thickness of the truss members, and so each member is just set. There's a uniform thickness across the truss, and it's equal to the width that needs to be to hold that max load. So we then calculate the length of the truss all around. We start with the outside length, then we calculate it for each cross member. sum those up and find the mass, and then again there's our weight variable. So a number of these items are actually sent to the HouseTruss variables, as you can see here. So let's just go back and talk just for a second about design intent again. There's a number of ways we could have sketched this to actually draw it. And what you'll usually end up doing is drawing it one way and then altering it slightly as you move along, so that your design intent is more driven by the parameters you want it to be driven by. So a couple of examples of that are that it's tempting when you draw a truss like this to define everything either from the center out or from a side into the other side, or maybe from the bottom up. But those aren't the parameters that are driving the design of this truss. The actual parameters are the thickness of each member. That's what's important to us, because we want those members to be able to hold the stress, and then where these connection points are made. So if we want the brace to move up or down at any point, or the load changes and we want the thickness to change, the truss needs to be able to adapt to that without losing its shape. So if you're building from left to right and you're defining something by, say, a side of a member here, it's going to cause problems if there's a big change in the design. So what we've done is we've defined these connection points from outside in, and these connection points are defined by the variables that are sent from that truss document. We then used construction lines to ensure that to create a line that runs from the midpoint of this vertical connection to the connection point there, and then defined our defined the cross-sectional thickness here as out from either side of this middle construction line. And the thickness of the vertical ones is done the same way. There's a midline defined, and then the member is actually defined as extruding out from each side of that. The angle of the roof is pulled in. The height of the truss is pulled in. There's the angle. This was our truss height of 18 inches, which is the vertical distance from here to here. And you can see these variables here. If you haven't gone over the tutorial, what you do is you click this to enter a variable, and you then change its name. When you set up in CADWolf to send that variable to this element in this document, it will update any variable with the matching name. So Onshape builds its CAD models from top to bottom. So you just put all of your equations at the top so that they're there when you need them. And so when you go and make that sketch there, you've got all those variables available to you. You also notice that I've defined 4 planes here. That goes back to our design intent. So the middle of these vertical members is actually established by these planes. And these are these 4 planes. So these planes are defined outward from the center. So we send the width of the house, and then within Onshape we actually calculate this truss span here, which you see there is just a fifth of the width of the house. Since we have 5 what I call spans, which is one, this would be one here, this would be one here, the one in the middle, and the 2 on the right. So divide that by 5, that gives you the width of one of them if they're equally spaced. So we go a half truss span here, a half truss span here, and then 1.5 out to this plane and this plane. So if we have to change the width of the house, these planes will automatically shift inward or outward to accommodate that. The width or thickness of the truss members will obviously accommodate for that. You won't have to change these angles. Everything's set up to where everything alters itself automatically. You might have to go through a few iterations of the design to do that, but in the long run you're going to save yourself a lot of time by doing that. Alright, so the remaining part of the design is pretty straightforward. The weight from the dead load in the roof and the truss is then passed on to the riser, which is actually made of stainless steel. And then its cross-section is calculated to hold that load. So like we said, you can pull in the weight here. You can also pull in the material properties. You can see the block is concrete, the riser is stainless steel, these are defined in Onshape. You have to make sure that the density of the material you're using here will match the density you're using in your documents, so that the weight and mass comes out to be the same. Alright, so the benefit of doing this in CADWolf is that you have this organization for each part. You have the documents readily accessible, and you have access to the CAD file from here. You can compare the weights and masses to make sure that it's reasonable. You can do a number of organizational things here, but let's say you have all this done and then a parameter changes. Let's say your dead load doubles from 25,000 pounds to 50,000 pounds. So we go into our design document, our measurements and input document, change this, save it, and you're going to notice it starts to take a while for the save to be confirmed, because it's sending these parameters to that Onshape document and then waiting to get a response before it gives you the all okay sign. So you've changed the dead load, so you could change the factor of safety there too. And you go back to your part tree, update the statuses, and you see now the green has changed to red on all of these. So all of these documents pull in parameters from that file, and then it's telling you, okay, I might need to be updated because a file I depend upon has been changed. There's no guarantee that it alters the effects of these parts. It's just saying, hey, a file I depend upon has changed. So all we did was change the dead load, which I know isn't going to change these designs, so I'm not going to worry about them too much right now. Obviously, it changes the weight that the truss is holding. So from our part tree, we can simply tell the item to update. It goes and it pulls down all those equations, solves them, resaves that document, which then sends those parameters to Onshape. And it changes back to green to tell you that everything is up to date. The riser is going to have to be changed to accommodate this as well. Sometimes this can be a bit slow when you're recording video at the same time, obviously, but it will turn to green when it is complete. There we go. The design of the block isn't going to change much, but it is going to have an issue if the riser thickness changes. That hole needs to be changed. One other thing I would say is to make sure that your connection to Onshape remains valid. Sometimes it will become invalid if you haven't used it in a while. Let's just re-update that one to make sure it got sent. It took that took a long time, which often means that connection got spoiled. Alright, so let's hit enter here again. And you saw these parameters obviously updated. Let's go back and see if so the data in the CAD model may have changed, but these numbers haven't updated automatically. You have to go in and tell it to pull in the masses, and you'll start to see these change. There you saw the top one there change, and those numbers match pretty closely. So we go back into our CAD model, and you can't really tell the difference. I know that this number was roughly 3.6 before we doubled that dead load, and now it's 4.2. So the thickness didn't change enough for you to see it on the CAD model, but it did change. The thickness of the riser changed as well, and the inputs to the block changed as well. So what we were able to do there is a complete redesign of the truss and the riser and the block based just upon changing that one parameter that changed and then clicking the updates. That saves a massive amount of work and time, and then we were able to verify that those changes were all consistent across the CAD and the documents and get sort of instant feedback on it. So the documents within this workspace, along with the part tree, will help you organize your designs. The workflow, which isn't really used much here because it was just me designing this, will help you in groups to organize the design of things. So he pulled in the design documents and then the part tree. You'll see a star there which shows you the date of each one that's created, so you can see when the designs are created. The little save icon indicates when it was saved. You can turn these off and on because it's going to get crowded if you're saving a lot. What you do in a workflow is it's similar to a Gantt chart. You create events. Your versioning can be controlled from here if you would like it to be. So you can create sign-offs as well. A sign-off would be something like you need an engineer to sign off on the design of something and then lock it. You can task them with doing it from here, set all that up. You'll see events in the workflow as they've been taking place. So as you decide things need to be set a certain way, you can do all of that here. So this coordinates the process of the design. So this, coupled with the structural design in the part tree itself, should be able to control most of your engineering process. And I think that's it for our truss. You can get to the CAD model from the link here in the description, and all these items should be publicly available to anyone.